In this video, we're going to continue looking at practice problems in section 8.3, introducing partial derivatives. So our first example is we're going to look at heat index. So the table below, we're going to call the heat index capital I in degrees Fahrenheit, and that's going to be a function of H and T. H is the percent humidity, it's relative humidity, and temperature is going to be in degrees Fahrenheit. So the temperature is the actual temperature outside, and then our function I, which is going to be little f, is going to be what it feels like, the heat index. So we've looked at an example like this before using a different table. Note that these values over here are not there, and that's because these temperatures are too large to kind of think about in terms of what it feels like for humans, as it doesn't really make a difference at that point. It's too extreme. In fact, some tables might not even have these other values here because they're too extreme. But it depends on what you're looking at there. So our question, it says, let's look at the derivatives. And again, there's two derivatives, one with respect to temperature and one with respect to humidity. And we're going to look at the temperatures or the derivatives at a specific point, and that is when H equals 20 and T equals 75. So that is corresponding to this part of the table right here. H equals 20 and T equals 75. And we're going to look at both the partial with respect to T and the partial with respect to H. Let's recall that this notation is the same thing as saying F with a little subscript of capital T, and this is F with a little subscript of capital H. Just different notation for the partial derivatives. So to estimate this, we're going to have to use the table of values. And note for the first one here, for A, we're going to look at with respect to T, so we're going to go over in the T direction. We're going to look at what happens if we go a little bit in the T direction. So what we could do is we could use those values and say that the derivative at H equals 20 and T equals 75 is going to be about the change in the function value over the change in the input, the change in the output over the change in the input. So that is going to be 77 minus 72 over 80 minus 75. Again, that's the change in the function values over the change in the inputs. In this case, the inputs are our T values. And this will give us a 5 over 5, a positive 1. Now that's just an estimate with the given values that we have. We could have also gone in the opposite direction and said maybe that F of capital T of 2075, we'll write out some more detail here, could be F of 2070 minus F of 2075. Doing this in a different way, we could look at F capital T 2075 is going to be F of 2075 minus F of 2070 over 75 minus 70. Now what this is doing is looking at the value before that 2075 is. That's just as important as looking at the value after. So this would give us a 72 minus 66 over 75 minus 70, which would be a 6/5. And both of those would be acceptable answers as to what is the derivative at this point. Since we don't have more values, we just have to use what's in the table. And the actual value of that derivative may be the average of those two values. That's a common thing to kind of do to see a better estimate, is take the average of these two values, 1 plus 6/5 divided by 2, which would be 5/5 plus 6/5 divided by 2, 11/5 divided by 2, or 11/10. Now I'm going to say that any of these values, +1, +6/5, +11/10, all those are acceptable answers as to estimate that derivative, and just different ways of doing it. But again, we're looking at the values above and below that specific value we're starting with, and in the direction of t. Now let's do the same thing, except now we're going to look at with respect to h. So our first one we're going to look at is, here's our value right here, 72. We're going to look at the positive direction. So we're going to look at those values. And again, this derivative, f of capital H, 2075, is going to be about f of 20, sorry, not f20, f of 3075 minus f of 2075 over 30 minus 20. So now our inputs here are these humidity percentages, 30 and 20, and then our outputs are given by the same things in the table. So this will give us a 73 minus 72 over 30 minus 20, or 1/10. Again, we could do a similar thing as we did before. We could look at the opposite directions. That is maybe looking at the value before. So that would be f of 1075 minus f of 2075 over 10 minus 20. Or we could flip those values. Either way, we would get a 70 minus 72 over 10 minus 20. Here's a -2 over -10, or a +1/5. And again, we could take the average of those two values. 1/10 plus 1/5 divided by 2, which would be 1/10 plus 2/10 would be 3/10 divided by 2, or 3/20. And all those values would be appropriate. Note that one thing I did here, and this is true always in just a calculus kind of thing, is it doesn't matter what order you write those function values, f of b minus f of a, as long as you're consistent. So here the 10 worked with the 10, the 20 with the 20. I can't go f of 10 minus f of 20, and then 20 minus 10 on the bottom. But here we had negatives in both parts, and they canceled out to give us a positive. So looking at this and what this actually means, right, this is saying that if you increase the temperature at this point, the heat index is going to go up, right? If we look at just the value of 1, we're saying that if we increase the temperature by 1 unit, the heat index should go up by 1 unit at this point. But that's going to be different for different values that we have. And if we increase the relative humidity by 1%, we should increase the temperature by 1/10 of a degree, or 1/5 of a degree, or 3/20, depending on which value you want to use. In this case, we are increasing with respect to humidity and temperature. Now let's look at an example where we look at contour diagrams instead of a table. This is our other way of looking at a function of two variables. So the figure below shows a contour diagram for the monthly payment P as a function of interest rate, R, and the amount L of a 5-year loan. We are going to estimate the partial of P with respect to R, and again, note this is the same thing as P sub R, and the partial of P with respect to L, or P sub L, at the point where R equals 8 and L equals 5,000. And we're going to give the units and the financial meaning of our answers. So we're going to do the exact same thing that we just did, except now we have to interpret what are the function values given this contour diagram. So to start with, let's actually find out what point we're going to be looking at. R equals 8, L equals 5,000. So that is a rate of 8% and a loan of $5,000. So we look at 8, 5,000. We're looking at this point right here. And it seems like that if we look at P of 8, 5,000, we should have a value of 100 because we're on that contour of 100. So that's saying a rate of 8% for $5,000 for a 5-year loan, then we should have a monthly payment of $100. Okay, to think about these derivatives, we're going to focus on either R or L at the same time. And let's focus on R first. So we're going to look at dp dr, the derivative with respect to R. We're going to fix L equal to $5,000. So our whole world is just going to be on this line. That's all we're focusing on. We're thinking about a function of one variable. And what I want to do is it's just going to be an estimate, but we're going to try to find two function values and then divide by the corresponding inputs. So we already have one of those. How about P of 8, 5,000. And we're going to look at another function value. The only other one to really have to look at is maybe this point right here, because I know what the function value is that. It lies on a different contour. That's why we're choosing that one. That might be P of 15, 5,000. Again, our whole world is just on that red line, and I need to find 2 points that I know the function value. So I need to find 2 contours that pass that line. This is just like in our table, we needed the 2 values that were given, is just our given values here. And then we're going to divide by our inputs there, our R values, 8 and 15. So here we have that our values are going to be 100, which you found before, minus 120 over 8 minus 15, which should be negative 20 over negative 7, or 27ths. We'll talk about what that means after we find dp dl. So dp dl, if we think about it in the opposite direction, now we're going to focus on fixing 8 r equals 8. And we're going to think about everything lying on this line, and we need 2 points on that line. So let's use that point right there. So we have our 2 points. So we could look at this as going to be estimated by P of 8, 5,000. That's one of our points we can use. Minus P of 8, 4,000. And again, this time we're looking at now the L value. So that's going to be our inputs, 5,000 minus 4,000. And that's going to be 100 minus 80. 80 because we're on this contour that corresponds to 80. Over 5,000 minus 4,000. 20 over 1,000, which is the same thing as 2 over 100, or 1/50th. So what do these mean in the context of the problem? So dPdR is saying at a loan of 5,000 at 8% interest, if we increase the interest rate by 1%, the monthly payment increases by 20 over $7, which is about $3. All right, so if you increase the rate by 1%, if you go to 9% instead of 8%, you should expect the monthly payment to be $103 instead of $100. And for the other derivative, we have at the same starting point, so at a loan of $5,000 at 8% interest, if we increase the loan amount $1, the monthly payment increases by 1/50th of a dollar. And that might be kind of odd to sort of say, so maybe a different way of saying this is that if we increase the loan amount by $50, just multiplying by 50, the monthly payment should increase by $1, which makes a little more sense instead of thinking about 1/50th of a dollar. And you could do that for any value. You could say, what happens if you increase by $1,000? We should expect the monthly payment to increase by 1/50th times 1,000, which would be $20. And you could do any kind of increment in between. We usually just choose one, but sometimes there's nicer values to choose. In this case, the monthly payment function is increasing with respect to R and with respect to L. And that is looking at the sign, the SIGN, the sign positive negative of the derivatives at those points. In the next section, we're going to look at computing these partial derivatives algebraically. Given functions, how do we find these derivatives, and then more about what they mean.